Welcome to Empowered Learning. This is the second video in the video series for learning how to apply the ratio and root test for absolute convergence of an infinite series. So in the part one video, we saw what the ratio test was, what the root test was, and we saw a few examples that were already worked out so that we can kind of see how to work with it. So in this next set of examples, we're mainly going to try to use the ratio and our root test, but when necessary, we will use other things like recognizing that we can use the integral test or comparison test, alternating series test, or even recognizing that we have a geometric series, a P series that converges, or a P series that diverges, to help us be able to figure out whether the given series that we're dealing with actually converges or not. So in this first example here, we see that we have the series of 6 divided by n minus 6 divided by n cubed. I'm sorry, this is n squared, sorry. So here, the first thing that we know is that since we have the difference of two sequences in our series here, we could rewrite this as summation of n equals 1 to infinity of 6 divided by n, and then we can write this other series this way. Okay, now in doing this, we can see that our first term here, this looks like a harmonic series. And if I was to actually factor out this 6 here and put it on the outside, that would be 6 times that. And if I did the same thing here, then I would have 6 here and 1 there. So we know here that what this is actually the harmonic series. And we see here is a P series, where P is equal to 2, which is greater than 1. So we know that this P series here converges, but here we know the harmonic series diverges. So because we have the difference in a divergent series and a convergent series, of course, because the divergent one is just going to keep on going to positive infinity, we know that this particular series here is ultimately going to diverge. Okay, so we'll say here that our series diverges, and so we could easily figure that out because of the fact that we recognize that the actual series that we had could be broken up into the difference of two series, where one of them was a harmonic series, the other one was the P series. Okay, so for our next example here, we see that we have this series that is n plus 3 factorial divided by 3 factorial times n factorial times 3 raised to the n. And so for this particular one, of course, if we look at it, if we go and look at our checklist here, we know that it's not a geometric series. We know that it's not a P series, so we kind of know that, all right, those two things are not going to work. And here we do the, basically take the limit of the sequence to see, is it going to go to 0 here? If we go back and check it, that just at quick glance, not exactly sure if that's going to be the case here. Because of the fact that you have an n factorial, times 3 raised to n in the denominator, and then you have n plus 3 factorial in the numerator. We may not know if that goes 0 just by quick glance. So the easiest thing to do in this situation is to actually go to step number 4 and actually try the ratio or root test. And so in this instance here, the ratio test would probably be the best thing to do. So what we're going to do here is identify what our a sub n is. So that'll be, I'm just going to rewrite what we have there. And then of course, our a sub n plus 1, everywhere where we see n, we'll replace it with n plus 1. All right, so now that we have that written here, remember what we are essentially trying to do is evaluate the limit as n approaches infinity of the absolute value of a sub n plus 1 divided by a sub n, and to see what that outcome is going to be. So to do that, first we need to figure out, well, what is going to be absolute value of a sub n plus 1 divided by a sub n, okay? So we'll start off by evaluating or figuring out what that's going to look like in its simplest terms here. So we'll rewrite the a sub n plus 1, and of course, if we simplify what we have here, this will be the same as n plus 4 factorial here, all over 3 factorial. And then we have the n plus 1 factorial here, and 3 raised to the n plus 1, okay? And I'm going to clean up this to make it look a little bit nicer. All right, and so now for the divided by a sub n, that's the same as the reciprocal of what we see here. So this will be 3 factorial times n factorial times 3 raised to the n, and in the denominator we'll have n plus 3 factorial here, okay? So now what we need to do is to simplify this as much as we can. And so the first thing that we see is that for this n plus 4 factorial here, notice that we have n plus 4 factorial in the numerator, but n plus 3 factorial in the denominator. And if you remember about factorials, n factorial is just n times n minus 1 factorial, or if we wanted to keep on going, it will be n times n minus 1 times n minus 2, and we just keep on going till we get to 1 here. So my point is that if we were to list out the first factor in this n plus 4 factorial here, we would just have n plus 4. And then we could rewrite the rest of that as just n plus 3 factorial, okay? And so I'm going to rewrite the rest of my denominator for this one. Okay. And so for this n plus 1 factorial, if I go ahead and list the first factor out for that, that'll be n plus 1 times n plus 0 factorial, which is just the same as n factorial, okay? And then here, 3 raised to the n plus 1 is the same as 3 raised to the n times 3 raised to the 1, which is just 3. So I'll go ahead and erase that. So now that we have that, then we multiply that times 3 factorial times n factorial times 3 raised to the n, all over n plus 3 factorial. And so now we're at a point to where we can reduce some things to 1 here. So to start off, we know that this n plus 3 factorial and this n plus 3 factorial will reduce to 1. We also have this n factorial and this n factorial reducing to 1. we have this 3 raised to the n and this 3 raised to the n reducing to 1. We have this 3 factorial and this 3 factorial reducing to 1. And so here, what we end up having left after all this be n plus 4 divided by this 3 times n plus 1. Okay, so that will end up being, and here I didn't write this, but I probably should have these absolute value signs here. It turns out that for this particular situation, since we're dealing with the factorials and the exponentials here, that everything ends up being positive anyway. But just to be formal, I'll go ahead and write those absolute value signs in there. And since n will be natural numbers, this whole thing will be positive. So we'll just have n plus 4 divided by 3 times n plus 1. And so now that we have what this expression of absolute value of a sub n plus 1 divided by a sub n is, then when we go and evaluate the limit, we see that this is going to be something relatively easy to evaluate. So this will be the limit as n approaches infinity of n plus 4 divided by 3 times n plus 1. If we factor out the understood 1/3 that's there, and we have the n plus 4 divided by n plus 1 left over. If we look at this as a rational function, this limit as n approaches infinity here just means we're trying to find out if this rational function has a horizontal asymptote, and it does at y equals 1. So this particular limit here will all just go to 1, and our final answer there will end up being 1/3, and that is less than 1. And so because our limit here is less than 1, we know that our original series is convergent. So I'm just going to say here, therefore, series is absolutely convergent, which implies that series is convergent. And again, I'm just doing a shorthand here. The series that I'm talking about is the original one. So this particular series will be convergent. All right, so let's move on to the next example. Okay, so for our next example, we see that we have a series here, and it has this alternating factor here for the signs. So automatically, if we go back and we look at our checklist here, we know that we may have to consider doing the alternating series test. So because of that, of course, the first thing that we want to see is the series that we're dealing with, is it absolutely convergent or not? So we want to either use a ratio or root test to be able to test for absolute convergence first. Okay, we kind of skipped all of these because of the fact that we know it's not a geometric series, know it's not a p-series, and of course, when we look at this and we try to take the limit of this as n approaches infinity, just for this portion of it, of course, the fact that we have this part right here is going to make it oscillate back and forth in between positive and negative, which in itself on its own is going to kind of disqualify the nth term test for divergence. But if we were just looking at this, the limit of n divided by 5n cubed plus 1, that would go to 0 because the degree of the denominator is larger than the degree of the denominator of the numerator. So we're still in a case where the nth term test for divergence is inconclusive anyway. Okay, so that's why we're going ahead and skipping here to step number 4, and we're going to try the ratio or root test, whichever one probably applies a little bit better. If this doesn't work for us for absolute convergence, then we'll come down here and do the alternating series test to test for conditional convergence. So that'll be our strategy for this particular series to test for its convergence properties. So let's start off by, of course, first identifying what a sub n is and what a sub n plus 1 is. So a sub n is just going to be the actual sequence itself that is making up the series. And of course, a sub n plus 1, this is going to be everywhere where I see n, I'm going to do n plus 1 here. So this will be negative 1 raised to the n plus 1, which will be n plus 2, and then times n plus 1 over 5 times n plus 1 cubed plus 1. Okay. So therefore, we need to now figure out what absolute value of a sub n plus 1 divided by a sub n is. And so this is going to be wrote the wrong one there. So let's get the correct one there. So that would be that. And this will be n plus 1 here. And this denominator this will be 5 times n plus 1 cubed plus 1. So that is our a sub n plus 1. And we're going to divide that by a sub n, which is just going to be the reciprocal of what we have here. So that's just going to be this negative 1 raised to the n plus 1 times n in the denominator, and 5n cubed plus 1 in the numerator. Okay. All right, so if we do the absolute value of this, we know that all these terms except for the negative 1 raised to the n plus 2 and negative 1 raised to the n plus 1, those things may be negative, may be positive. So we're basically just going to strip those out. And so what we're left with is just n plus 1 times 5 n cubed plus 1. All that over 5 times n plus 1 cubed plus 1. And all of that times n. And so now what we need to do is to do what we can to simplify what we have here so that we could take the limit of that. So here I could rewrite this as n plus 1 over n times. So now I'll have 5n cubed plus 1 over 5 times n plus 1 cubed plus 1. And so this n plus 1 over n, we could simply rewrite that as 1 plus 1 over n. And here for this next factor, what I could do to make things a little bit more simple is I can multiply the numerator and denominator by 1 over n plus 1 cubed here. So, and I'll go ahead and try to fit it in here. And we'll use a different color here. So I'm going to come here and we're going to multiply this by 1 over n plus 1 cubed. And same deal here. 1 over n plus 1 cubed. And all right, so we need to put that back in there, then equal sign. And so if we have that, then of course, what we would get in the numerator here would just be a 5 times n cubed over n plus 1 cubed plus 1 over n plus 1 cubed. And in the denominator, what we'd end up having is 5 plus 1 over n plus 1 cubed. So I have all of this. And so at this point, we have this in a form to where it'll be relatively easy for us to take the or evaluate the limit of it. The only other thing that I would suggest doing here at this point is let's go ahead and change what we have going on here. So because of the fact that both of these, the n and the n plus 1 are raised to the 3 here, I could just get rid of this exponent here and just have this be n divided by n plus 1, all of that raised to the 3. And that would make writing the next steps a little bit easy. So therefore we have limit as n approaches infinity, the absolute value of a sub n plus 1 divided by a sub n equals, and then it's just limit as n approaches infinity of 1 plus 1 over n times limit as n approaches infinity of all this business here. Okay, and so now at this point, to kind of make life a little bit more simple for us here, if I was to evaluate the limit of what I'm seeing here, I'm going to come down here and do it, we would see that we would have 1 plus 1 over infinity, and of course that 1 over infinity here goes to 0. We also have here, basically, if we put infinity wherever we have the n's here, of course this n divided by n plus 1, if we take the limit of that as n approaches infinity, that's like asking if we have a horizontal asymptote. So I'm going to write it like this, because we need to be kind of formal here whenever we do it. Point that I'm trying to get to here is that if I take this limit of n divided by n plus 1 as n approaches infinity, that result is just going to be 1. Okay, and we take all of that, cube it, plus, and then over here this would be 1 over infinity plus 1 cubed. I'm going to go ahead and write that in, and then 5 over 1 over infinity plus 1 cubed. Of course, this limit here would go to 0. This limit would go to 0. Here, if we were to stick in infinities for both of the n's, we would just basically have an infinity over infinity. And if we did L'Hopital's rule with the n over n plus 1, then the derivative of both of those is just 1. So the limit of n divided by n plus 1, all that would just end up being 1 there. Okay. And so with that, our result ends up being just a 1 times, over here we have 5 times 1 cubed, which is just 5, plus 0 over, and then we have 5 plus 0. So we have all this. Of course, this goes to 1. So we just have 1 as our answer. And unfortunately, what that means for us is that this is inconclusive. Okay. So we did all that work, and unfortunately, it just means for us that we ended up seeing that our series is not going to be absolutely convergent, but we can now look at the alternating series test to see if it's going to converge conditionally. Okay. So if we go back and look at this, we need to basically compare the n divided by 5 n cubed plus 1 and see, all right, well, does these terms here, as we make n higher and higher, or is this b sub n that's right here going to be ultimately decreasing? Okay. And it will. Okay. And we know that there's a couple of ways I can actually prove that to you, but the easiest way I can tell you here is that if we look at the function 5n cubed plus 1, and then look at the function y equals n, 5n cubed plus 1 is always going to grow faster than n. So the limit of this is going to go to 0. Okay. And so if I keep on listing out numbers here, I would see that every single time that I write something, this 5n cubed plus 1 is going to be way, way bigger than n. So there's no way that this is going to catch up with it. Okay. So in short, what we need to do is be able to show that n divided by 5n cubed plus 1 is going to be ultimately decreasing. And we need to show that the limit of n divided by 5n cubed plus 1 is going to be going to 0. And if so, then we know that this particular series will converge conditionally based on the alternating series test. Okay, so here I've rewritten our series here, but of course I've written it in a form to where we've identified the portion that is non-negative, which is the b sub n here. And so the first thing that we want to do is show that basically that b sub n plus 1 is going to be values that are less than b sub n, for some value of n 1 or higher. And it could be, let's say, we could have n equal 10 before it starts to do this, but at some point, it just needs to happen. So if we go and actually just start listing terms here, let's say if I do b sub 1, b sub 2, and b sub 3. So b sub 1, if I was to do this, will be 1 over 5 times 1 cubed plus 1, which would just end up being 1/6 once I'm done with everything. If I do it again here, then this will end up being 2 over 41. And if I do it again here, that would be, looks like 3 over 136, I believe. Okay. If I was to approximate what these equal here, this would be approximately 1.67. 2 over 41 is approximately 0.048, and 3 over 136 would be approximately 0.0221. And so we can see that as n gets higher, the actual value of the numbers in the sequence that's made up of b sub n is getting lower and lower. So this lets me know that b sub n plus 1 is going to be smaller than b sub n for all values of n in the natural numbers. Okay, so we know because of this, I can also say that. So this first criterion is checked. Okay, so the second criterion is that we need to see is the limit as n approaches infinity of b sub n going to be equal to 0. Okay. And so here, we'll just go ahead and evaluate that. And so our b sub n here is just going to be n over 5n cubed plus 1. And if the limit of this function as n approaches going to infinity, if that's what we're doing, again, is asking, do we have a horizontal asymptote for this? Another way that we can look at this is that we know that the numerator and denominator act like polynomials. And of course, this function would actually behave like n over 5n cubed for very large values of n, which we know if we did some simplification here, would just be 1 over 5n squared. And if we were to plug in infinity here, we know that 1 divided by 5 times essentially infinity, all of that is just going to go to 0 here. Okay. So second criterion, which is the limit of this b sub n here as n approaches infinity, goes to 0. So we've met 1, we've met 2 criterion. So basically this means, therefore, our series is conditionally convergent via the alternating series test. So we see in this example that, again, we could not show that our series was absolutely convergent, but because of the fact that it was an alternating series, it will be conditionally convergent. And again, if you remember what that means that if we were to take out all of the terms of our series here and separate them into terms that are negative and terms that are positive, all of the negative terms, if we add them up, will go towards negative infinity. All of the positive terms, when we add them up, will go towards positive infinity. And if we summed up all the sum of the negative terms and the positive terms, assuming that the infinities are of the same size, infinity minus infinity, if infinity is thought to be around the same size, should be approaching 0. Okay. And so that's what conditionally convergent means. Okay, so for our next example here, we see that we also have another alternating series that we need to deal with here. And because of that, we also know that this is probably going to be our b sub n that we're going to deal with here. So let's go ahead and use the ratio test again to see if this is going to be absolutely convergent or not, or if we're going to be able to find out that it's just straight up divergent. Okay. Hopefully it will be one of those two. So our a sub n here is just going to be negative 1 raised to the n plus 1 times this 3 plus n over 5 plus n. The a sub n plus 1 is going to be negative 1 raised to the n plus 2, because everywhere where we see n, it'll just be n plus 1 times n plus 1 plus 3 will be n plus 4, and that'll be divided by 5 plus n plus 1, which will be 6 plus n here. And so therefore, our a sub n plus 1 divided by a sub n, and we'll do the absolute value of that. We already know here that the negative 1 raised to the n plus 2 and negative 1 raised to the n plus 1 is going to go away whenever we have the absolute value sign. So we're just going to ignore those. And so here we'll have n plus 4 divided by n plus 6. I'm going to go ahead and turn it around. And we're going to multiply that times the reciprocal of 3 plus n divided by n plus 5, or 5 plus n. So I'm just going to turn them around. So this will be n plus 5 divided by n plus 3 here. Okay. So this is essentially what we end up getting. And so here, if we wanted to evaluate the limit of each of these, this is at a point where we can do that. So here, this would be limit of n plus 4 over n plus 6 times limit of n plus 5 over n plus 3. Okay? And of course, since I have the product of two functions, if I take the limit of the product, it'll be the product of the limits. And again, for the same reasons as before, we know that limit of a rational function as n approaches infinity just means, hey, we're trying to figure out if this has a horizontal asymptote, and it does at, let's say, y equals 1. So this limit will go to 1. This limit will go to 1. So, of course, here, this is going to be inconclusive. So we are going to have to use the alternating series test again to determine whether this is going to be conditionally convergent or not. So to do that, of course, we look at our the 3 plus n divided by 5 plus n, which we're calling our b sub n here, and we need to list out those values to see what it looks like. So here, let's say our b1 is going to be 3 plus 1 over 5 plus 1, which is going to be 4 over 6, 2/3. Our b sub 2 is going to be 3 plus 2 over 5 plus 2, which is going to be basically 5 over 7. B3 will be 3 plus 3 over 5 plus 3, and that will be 6 over 8, or 3 over 4. And notice here that 2/3, that number is roughly 0.67 here. We also see that 5 over 7 is roughly around 0.71. And of course, 3/4 is exactly 0.75. So let's try to get rid of that. So what we see here is that as n increases, we see that our values of b sub n also increase. So the fact that b sub n plus 1 is less than or equal to b sub n, that's not being met here. So this particular series is not going to meet the conditions of the alternating series test. And so since this is an alternating series and there's no other test to kind of go with it here, we're going to have to basically say, therefore, this series diverges. Okay, because again, we know that it's not absolutely convergent because it failed the ratio test. We see here that for the alternating series test, that was kind of our last hope, and we see that it actually failed that as well. So there's nothing else left to try, and we know from that that this series is going to have to diverge. Now, another thing that we can also state here for this situation, and the reason why I didn't to start off with is because of the fact that we had this factor in here that makes it an alternating series. But remember, in general, if we have a series, and we're going to assume here that all of the terms of the sequence that forms the series has positive values to it. Remember, the nth term test for divergence could have also told us here that this particular series diverged. And so how we could have done that is, of course, unless the limit of the sequence that makes up the series goes to 0, we know that this particular series will diverge. Now, we couldn't do that directly because we had this in here. And my point is that anytime we have this alternating factor here, it's going to make every limit be a does not exist type case. Okay. So we can't really look at this portion here on its own and just say, oh, yep, it automatically is going to diverge because the limit of a sub n is going to not exist. Okay. But if we look at the limit of b sub n, which is essentially just saying the limit as n approaches infinity of n plus 3 over n plus 5, we know for the same reasons that the limit of n plus 4 divided by n plus 6 is 1, the limit of this is 1 as well. Okay. So looking back here at the nth term test for divergence, we see that the limit of the sequence a sub n in this case, we had in our problem, it actually went to 1 and not 0. So here by the nth term test for divergence, we know that since the limit of our sequence went to 1, and again, we're just assuming that we're ignoring the oscillating part of the signs, that alternating factor. We are forgetting about that part, but just looking at everything else, we see that this particular series ends up diverging because of the fact that the sequence itself does not end up going to 0. Okay, so that is another quicker approach that we could have taken to figure out what the answer to this one is, but I kind of had to go through the whole thing of the alternating series, well, the ratio test and then the alternating series test to show you that, hey, even if we do it the long way or the short way, it's going to end up being the same thing. All right, so for our next example here, we see we have a series where the corresponding sequence that formulates the series is cosine of n pi divided by n times square root of n. And so here, one of the things that we want to notice is that, let's say if n is equal to 1, then cosine of pi is going to be minus 1. Okay, but if n is equal to 2, then this would be cosine of 2 pi, which is the same here as cosine of 0. And pen is dragging here. Cosine of 0, which is the same as 1. Okay, so my point here, and I'm going to go ahead and write out a few more of these to kind of make my point. So cosine of 3 pi is going to be the same as cosine of pi, which is -1. And sine, when n is equal to 4, cosine of 4 pi is going to be the same as cosine of 2 pi, which is the same as cosine of 0, which is 1. So we see we have basically cosine of n pi is another way of basically saying that we have -1 raised to the n. So here we could rewrite this as just -1 raised to the n, all that over, and this n times square root of n will be n raised to the 3 over 2. Okay, so that's another way of being able to express this particular the sequence in the series that we're dealing with. Okay, so now that we have that, we know we have an alternating series here, but because of the fact that we have an alternating series, we could do the ratio and root test here, but notice that in the denominator, we have n raised to some number. So what this kind of looks like is a p series, okay? In particular, what we're looking at here is an alternating p series, okay? And so since we're looking at an alternating p series, we could use the alternating series test to see whether this is going to converge or not. So here, what we could do is look at this series as summation n equals 1 and we'll say that this is 1, -1 raised to the n times b sub n, where this b sub n here is just the 1 divided by n raised to the 3/2. Okay. All right. And so once we have that, then the first thing that we need to check is for the alternating series test is b sub n plus 1 less than or equal to b sub n for at least some value of n that's 1 or higher on to infinity. Okay. And so in this particular case, we know that if we plug in 1 here, so if I have b1, I know that this particular situation here is going to be 1 divided by 1, which is 1. If I plug in a 2 there, this is going to be 1 divided by 2 raised to the 3/2. And just to make a long story short here, I know that 2 raised to the 3/2, which is just basically square root of 8, is going to be larger than 1. So because of that, I also know that b2 is going to be smaller than b1. And that's just going to keep on going here. Okay. So I'm just going to write it like this. So my point here is that we do see that b sub n plus 1 is going to be less than or equal to b sub n for all values of n that we're considering. Okay, that's one thing. And then, of course, here the limit as n approaches infinity of 1 over n raised to the 3/2. Of course, if I also plug in infinity into that, of course, all that's going to 0. Okay, so we know that by the alternating series test, if we do it in its pure form here, that because our b sub n sequence satisfies this criterion as well as this one, we know that our series here is going to converge. Okay, but it's going to converge conditionally. Okay. All right, so let's look at our next example. So for this example, we see that we're not given the summation form of what the series is. We're actually going to have to come up with that ourselves. So if we look here, we see that we have 1/12, -1/18, 1/24, -1/30. And you can kind of pick up here that what's going on is that, first of all, we have alternating series going on here. So if we were going to write this out, of course we'll have a summation here, and this will be -1, and since our first term here is positive, we can say that this is n minus 1 here. Okay, so the next thing, if we look at this, we know that 12 is the same as 6 times 2, 18 is 6 times 3, 24 is 6 times 4, and 30 is 6 times 5. So we can kind of see the pattern going on here. So we know that we're going to have a factor of 1/6 here. So I'm just going to take this and divide it by 6. Okay. And here we know that we have 2, then 3, then 4, then 5. And if this is the first term of the corresponding sequence that we're dealing with, if n is 1, then let's say our b sub 1 is 2, which will be the same as 1 plus 1, or n plus 1. Okay. And of course, if this next one here is n equals 2, then we would have our b sub 2 would be the same as, well, so b sub 2, which is just going to be this part here, which will be 3, which is the same as 2 plus 1, or n plus 1 again. So the point that I'm trying to make is that we know that our denominator here is just going to be, 6 times n plus 1. So here, what we can come here and do is just rewrite this as 1 over 6 times n plus 1. Okay, and so that is what our corresponding series in summation form would be like. And we can just make this go from 1 to infinity here. Okay. So again, we have an alternating series type situation here. We could do the ratio or root test to see if we're going to have a situation where we have absolute convergence, but more than likely that is not going to be the case. Now, how do I know that? Just simply put, if I come up with a sub n and a sub n plus 1, if I have a sub n, it's going to look like this. A sub n plus 1 is just going to be 1 over 6 times n plus 2. And if I was to take n plus a sub n plus 1 and divide it by a sub n, what I would get whenever I do this here, and I'm just going to go ahead and do it so you can kind of see where I'm going here. So we'd have this times the reciprocal of that. And what we would just have is n plus 1 over n plus 2. And of course, if I take the limit of this as n approaches infinity, it's going to 1. Okay, so we can do the ratio test and it's still going to be inconclusive. So the fact that we have alternating series here and there's nothing here that makes us think that, hey, this might possibly be absolute convergent, just tells us, all right, we need to just go straight for the alternating series test here. So for the alternating series test, remember we need to show that b sub n plus 1 is going to be less than or equal to b sub n. And for this one, it's pretty easy. And I'm not going to list these values out, but whenever we start plugging in higher values of n here, whatever we get is always going to be higher than 1, which means that the b sub n value is always going to be less than the b sub n plus 1 value is always going to be less than the b sub n value. In other words, for every, let's say, b1, b2, b3, we know that b3 is going to be a number smaller than b2, which is going to be a number smaller than b1. Okay, so we already know that. So our first criterion is satisfied. Of course, the final criterion here is that the limit as n approaches infinity of our b sub n, which is what this would be, would have to go to 0. And of course, that's an easy one as well. If we plug in infinity for n, we know that all this is just going to go to 0. So both of these are satisfied. So we know that we have conditional convergence via the alternating series test. Okay. All right, so for our last example here, we notice that we have a series here that's made up of a sequence where all the factors are raised to the power of n. So here, one thing that we can do is we could look at this as -1 times n minus 1 all of that for n, and then raise all of that to the power of n. And so since we have something raised to the power of n here, we could actually use the root test. So we're going to use root test. Let's try to make that look a little better. All right, so the root test says that we need to basically figure out what is going to be the limit as n approaches infinity of the nth root of the absolute value of a sub n. And we need to know, is that result going to be less than 1, plus or minus infinity, or greater than 1? Okay, that is the question. And so I'm just going to erase this and just put a question mark in general. But that's essentially what we're looking for. Of course, if it's equal to 1, then of course this using the root test would be inconclusive. So here what we need to do is figure out what this is going to look like. Okay. And first off, we know that because we have the absolute values here, the -1 here is essentially going to go away. So we're going to be having here is n minus 1 over 4n raised to the n, and this is going to be the nth root of that, which in the long run here is just this times 1 over n, which is just n minus 1 over 4n. Okay. And so for this particular situation, if we were to take the limit of it, so let's say limit of what we have going on here, which would be the same as limit as n approaches infinity of this n minus 1 over 4n, then here we know that both of these numerator and denominator act like the polynomial, where the leading term is going to be its behavior for large values of n. So we're going to have this situation here. And of course, these n's reduce to 1. And we essentially have the limit as n approaches infinity of 1/4. And the limit of any constant is just that constant. And that's less than 1. So therefore, we know that this series is absolutely convergent via the root test, which means that it's also going to be convergent via the root test. And therefore, series is convergent via root test. Okay. Now, you're probably wondering that, hey, if it's absolutely convergent, why do I have to go and state that it's convergent again? And so the reason for that is what we're saying when we say that the series is absolutely convergent. We're saying that if I basically strip out this alternating part of it and I look at that version of the series, then it's going to be convergent. But we know that if we strip out the alternating part of it and it's going to be convergent, then one of our basic facts basically told us that, hey, if we put the alternating sign part back into it, it's still going to be convergent. Okay. And so that's why we separate the two statements there, because again, all this statement is saying is that the summation of the absolute value of a sub n converges. Okay. And because we know this converges, that allows us to be able to say this too. But we can't jump automatically to, hey, the series converges without going through the fact that it absolutely converges first, since we use the root test to do it. Okay. All right. So with that being said, that concludes my examples and this series on using the ratio and root test to be able to prove absolute convergence. Hopefully you've seen how we use some of the other tests as well to be able to prove convergence, or in some instances, conditional convergence or divergence, depending upon what we were dealing with. So again, I hope that this helped, and I look forward to seeing you in the next video. And if you're watching these in order, the next video will be talking about a power series. Take care.